Chapter 3, Exercise 6. Show that a set A is a relation if and only if A is a subset of the cross product of the domain of A and the range of A. So, I think before we even start this question, there's a couple things we have to clear up, and it's regarding these two new symbols right here. So, dom A and ran A both refer to the domain of A and the range of A, respectively. And the formal definition for these is the following. So dom A is equal to X in the union of A, such that there exists some Y, such that X comma Y is in A. And then ran A, I'm going to define it as Y in the union of A such that there exists some X such that X comma Y is in A. And if you've done any rigorous mathematics before, particularly if you've taken an analysis class at this point, then you've probably done a lot of work with and proofs with domains, ranges, or sometimes they're called images and pre-images. So they're what you would expect them to be, only now we're defining them very rigorously from our notions of sets and arbitrary unions and so on and so forth. Right. As a quick aside, I think that Enderton really outdid himself with cringe notation. I don't know why he used ran for range. I've always just seen people write out the whole thing for range. If anything, I feel like you could shorten it to RNG, range A. I feel like that's a better abbreviation. Ran A just looks cursed. But anywho, my rant's over. I just wanted to point that out because it does bother me for no reason. Right. So let's get on with the proof. So let's assume first, or rather I'm just going to explicitly write out the structure of the proof. We're going to prove both ways. We're going to show that this implies this and that this implies this right back. So let's assume that A is a relation. Right? So, and remember that a relation is just a set of ordered pairs. So then if X comma Y is an element of A, then recall that this is how we define ordered tuples, specifically the Kuratowski definition is an element of A. Okay, so what are we trying to do right now? We're trying to show that every element of A is in the cross product of the domain of A and the range of A, assuming that A is a relation, right? So we have this. We're trying to show that this X is in the domain and that this Y is in the range, or yeah, pretty much. Okay, so now since yeah. Okay. I just wanted to add this quick lemma. I feel like I've just been working very rigorously with all the definitions. There are some shortcuts to be made. I prefer not to take shortcuts most of the time when doing math. I feel like one can get quickly confused if you don't follow the rigorous definitions as closely as possible. But I will say, especially when working with arbitrary unions, I think that there is some shortcuts to be made and that make life a little bit easier. Specifically, it's gonna be this is just a quick aside. If X is an A and A isn't, if X is in little a and little a is in big A, then I'm just gonna write it out logically. Then little x is in the union of A. I'm not gonna prove it. I feel like if you've done this, work with arbitrary unions enough, then it's pretty intuitive. Or actually, you know what? I did say that I'm not gonna rely on intuition. So let's just prove it. So suppose x is in A and little a is in big A. Then there exists some, actually the proof is so short, oh my god. Then there exists some little a in big A such that little x isn't little a. Thus, x is in the union of A. Right, so what does this mean? And why am I telling you this? So the reason I'm doing this is just that working with this definition is nice, but it's also kind of cumbersome. I don't like writing out quantifiers every single time I'm trying to prove something about the arbitrary unions. And I have done a couple of the exercises after this one. Turns out the unions show up a lot, especially in the context of functions, which is something I wasn't expecting, by the way. I just thought Anderton was just introducing these, like, I don't know, just random operations out of nowhere. But turns out they're pretty useful for defining functions, and then functions end up defining most of math in the end. So, you know what? I was humbled. I underestimated the power of the unions. Anywho, that sounds poetic. Underestimating the power of unions. Anywho, this is not a political video, so let's keep going. All right, why am I telling you this? It's just a nice way of like skipping over this intermediate step, right? And just like arriving at like the union. And it'll just, you'll see why it's useful. Okay, so what am I saying? I'm saying that x is in x comma y, and x comma y is in A. So we can deduce immediately that x is in the union of A. And now furthermore, x is an element of the set containing x, obviously. Oh yeah, and as we established earlier, set containing x is an element of the union of A. So this implies immediately that x is in the union of A. And this is where the lemma comes in. Otherwise, we would have had to write out this kind of stuff to justify ourselves the entire time, which is what I've been doing. And I don't know why I didn't think of this before, but it just makes life so much easier. Okay. With that said, we have x in the union of A, right? And then, similarly, let's set x comma y is in the ordered pair x comma y, which implies that, and x comma y is an element of A, which implies that this set is in the union of A. And moreover, y is in this set, and this set is in the union of A, so we can deduce that y is in the union of A. Okay, so what does this tell us? This tells us that, so for x, there exists some y in the union of A such that x comma y is in A, as we've established. Thus, x has to be in the domain of A. Now for y, there exists some x in the union of A such that x comma y isn't A, and thus y is in the range of A. And it's nice because this one arbitrary element we picked out from A ends up working for both of these, which is very nice. And actually, just because I want this to look neat, and because I forgot to say it earlier, I'm going to move these down, and I'm going to add our usual statement. Suppose x comma y is an element of A. You could have probably inferred that, but you know, I'm trying to be rigorous here. Okay, so x comma y satisfies that x is in domain of x and y is in the range of A. Sorry, x is in the domain of A and y is in the range of A. So x comma y has to be an element of the cross product of the domain of A and the range of A. Right, so A is a subset of the domain of A cross range of A, which is exactly what we wanted. Now, that's one side of one direction of the implication, or the biconditional. Now, this time around, we're doing it the other way around. So let's assume that A is a subset of dom A cross ran A. Right. Now, suppose little a is in big A, then little a is in A. I'm going to keep it to one inference per line. Okay, then little a is in A, which implies that little a is in the domain of A cross the range of A. Okay, so that's one inference. Thus, A must equal x comma y, some ordered pair x comma y, where x is in the domain of A and y is in the domain of A. No, y is in the range of A. There. Okay. So A is an ordered pair. So A is a set of ordered pairs. So ultimately A is a relation. Thankfully, this side of the implication was much easier to prove than the other one. Alright, in conclusion, A is a relation if and only if A is a subset of dom A cross ran A. And there you have it. That is chapter 6. No, chapter 3, exercise 6. I hope this was helpful, and I'll see you in the next video. Bye-bye.